The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Let's go to the lesson. So last day we studied VSEPR, which allowed us to infer the shapes of molecules, covalent molecules. Today I want to talk about the state of aggregation. What do I mean by state of aggregation? Is something a solid, a liquid, or a gas at a particular temperature? So 3091 is Introduction to Solid State Chemistry. One of the things we need to know is under what conditions is the solid state stable? And the state of aggregation, when it applies to covalent molecules, is going to lead us to a discussion of secondary bonding. So today's lecture is state of aggregation or secondary bonding. Now let's just reflect upon what we've learned up until now. We studied ionic bonding, and we knew that ionic bonding necessarily leads to crystal formation because we have unsaturated bonds, and that leads to an ion array of unlimited size until you run out of reagent. And something honking big made of ions is going to be a solid at room temperature. Last day, we appreciated that with covalent bonding, we have two options. We can either make discrete molecules, such as HCl, and HCl, as a discrete molecule, depending on a number of factors that I'm going to show you today, could be a solid, liquid, or gas. And we're going to understand more deeply how to sort out between the three of them. Or, I showed you at the end of last lecture, you could make a three-dimensional network, and diamond was one example. If it's a three-dimensional network that is a large array of solid, then that means you're going to end up with formation of a crystal, which is going to give you a solid. Diamond is solid at room temperature, graphite is solid at room temperature. So let's now go to the one case that we haven't dealt with, and that's the formation of discrete molecules. So let's look at discrete molecules. And what we want to understand is whether they're going to be solid, liquid, or gas at room temperature. And what's the relevant physics here in order to make that determination? The relevant physics is the following. We're going to compare two forces. We're going to compare the cohesive force between molecules versus the disruptive force. And the disruptive force in 3091 is always going to be thermal. It's thermal energy. And we know this. As we heat things, they go from solid to liquid to vapor as temperature increases. So thermal energy plays the role of the disruptive force, whereas the bonding is something that is the cohesive force. So let's go back to HCl. Last day we looked at HCl. So here's one HCl molecule. We have a covalent bond. It's a covalent bond within the molecule. We know this is a polar covalent molecule with the chlorine having a greater electronegativity and pulling the electrons towards its end. And furthermore, this bond I want to categorize as within the molecule, so I'm going to call it intramolecular. Intramolecular. Now, if I want to answer the question, is hydrogen chloride going to be a solid, liquid, or gas at room temperature? I don't have the information on the board. The only way I can answer that question is to put another hydrogen chloride. This simply forms the bond between hydrogen and chlorine. To determine whether hydrogen chloride is a solid, liquid, or gas, I need to look at how one hydrogen chloride molecule bonds to another hydrogen chloride molecule. So now this end is the delta plus, this end is delta minus, and we have, again, an intramolecular bond. So the question is, how does one hydrogen chloride bond to another hydrogen chloride? This is the intermolecular bond. Intermolecular bond. So intermolecular bonds govern the state of aggregation. And I'm going to show you the different types of intermolecular bonds. This intermolecular bond isn't the primary bond. The primary bond is here, inside the molecule. So the intermolecular bond is known as a secondary bond. Secondary bond. And there are three types of secondary bonds. We're going to look at them in turn. So the first one is depicted here on the board, and it's called dipole-dipole interactions. Dipole-dipole interactions. And these obviously occur only between polar molecules, operative in polar molecules. Not in, between. Take out in, operative between polar molecules. So we've made something covalent, and now how does one stick to the other? All right, and I think I've got a cartoon here that shows this. There we go. That's taken from an old book that I had. So you see the H and the Cl, and we have a dipole moment, and the negative end of one dipole is attracted to the positive end of another dipole. Okay, so we have a net dipole moment here, and we can measure the distance between the center of the dipole, center to center spacing, and call it R. Center to center dipole spacing, and say that the energy in dipole-dipole interaction, I don't expect you to know this by heart and do anything with it, but I just want you to realize that it's a weak force. This is very weak. It's proportional to the magnitude of the dipole moment. You'd expect that. Weak dipole moment, weak energy. Strong dipole moment, strong energy. Turns out it goes as the fourth order of the dipole moment, and it's inversely proportional to the separation. Only it's not Coulombic, it goes as 1 over r cubed, and there's a temperature factor, 1 over T. As temperature goes up, this energy goes down. And these are very weak forces on the order of about 5 kilojoules per mole. 5 kilojoules per mole. You remember what the crystallization energy of sodium chloride was? 787 kilojoules per mole. So this is very, very weak. It's operative at low temperatures, at very low temperatures. So for example, hydrogen chloride, in the case of hydrogen chloride, the melting point of hydrogen chloride is minus 115 degrees C, and the boiling point is minus 85 degrees C. You can see at very low temperatures, we already have enough thermal energy to disrupt. So if we have solid hydrogen chloride, the forces between the hydrogen chloride molecules in the solid are these very weak dipole-dipole interactions. And I think there's a couple more cartoons here. This is taken from your text, our text. So there we go. There it is. That's the soup that might be HCl liquid. Okay, so that's the first type of secondary bond, dipole-dipole interaction. Let's look at the second one. The second one is called induced dipole, induced dipole. Induced dipole, induced dipole. All right, and it's operative in nonpolar species. Dominant in nonpolar species. Why am I using the word species? Because I'm trying to be pedant and use fancy words. No, because I'm going to make it generic. I'm going to show it works in atoms and in compounds. So, as examples, what are some nonpolar species? Well, how about something like argon? Argon, if you look on the periodic table, it'll show you that it has a melting point of 84 Kelvin and a boiling point of 87 Kelvin. So if I cool argon to below 84 Kelvin, I get argon ice. So what are the bonds between one argon atom and another argon atom? It can't be this. There's no net charge. It can't be ionic. It doesn't form a covalent network the way diamond does. How do you justify the existence of solid argon? It's just so cold that it just sits there and freezes? I mean, how does it bond? There needs to be some kind of bonding. And other nonpolar species, so for example, the molecule iodine. Iodine melting point is above room temperature. It's a solid crystal at room temperature. Well, there's a strong covalent bond inside iodine, but how does one iodine bond to another and to another and to another? And we can even go to polyatomic species, such as methane. Such as methane. You know, there was the data from the Cassini probe. Look at this. This is an image from the Cassini probe. This is an island group. The yellow is an island group. The blue is a methane sea, a sea of liquid methane on the moon of Saturn, Titan. So There's liquid methane. How does liquid methane form? What causes one methane to bond to another methane? That's the question that we're wrestling with. So let's look at it first in a simpler context. I'll look at it with argon. So I'll put argon here. It's a spherical atom, and the question we have before us is how does one argon bond to another argon, as has to be the case in the solid or liquid argon. So we know that this has a lot of electrons, and the atom is net neutral, but the electrons are in motion. And so if I had an attosecond camera and I went in here and I went snap, I could catch a freeze frame where the electrons aren't symmetrically distributed around the nucleus. This nucleus is in, the atom is in constant fluctuation, but net neutral. Time average is symmetrical. So at some moment I might have a preponderance of electrons over here at around 3 o'clock. So this end of the argon atom is a little bit delta minus, which means the other end is delta plus. Now what happens if this is delta minus, this is delta plus? Can you see that the positive end of this argon atom will then pull on the electron distribution of the adjacent argon atom, rendering it delta minus at 3 o'clock and delta plus. So this is the dipole in one induces a dipole in another. And why does it occur in the first place? It occurs because the electrons are in motion. Electrons in motion lead to time-fluctuating dipoles. They're time-fluctuating. Time-fluctuating. Time average, there's no net dipole moment. I'm not going back on what I said before. There's no net dipole moment here, but this is time-fluctuating dipole. Time-fluctuating dipole. So, who was the first to explain this? The first to explain this was Fritz London. Fritz London in 1930. In 1930, Fritz London gave us the explanation because this troubled people for a long time. And he did so in a quantitative manner, and the mathematics of the treatment are identical to the mathematics for the dispersion of light under certain conditions. This has nothing to do with the dispersion of light. The mathematical formulation imitates the formulation of the dispersion of light, and hence the force here is known as the London dispersion force. London dispersion force. So people will say that solid argon is held together by London dispersion forces, or the bond is known by the name van der Waals. Van der Waals. We either call them van der Waals bonds or London dispersion forces. Van der Waals was Dutch. I know how to spell the word wall. This is the Dutch spelling, W-A-A-L-S, van der Waals. So in this system here, the London dispersion force, or the van der Waals bond, is in fact not the secondary bond, it's the primary bond, isn't it? It's the only bond. So by definition, it must be the primary bond. But can you see that in every compound, including diamond, we have time-fluctuating dipoles in all of the atoms? It's not just argon that has time-fluctuating dipoles. Every atom in you and me has time-fluctuating dipoles. But we're held together by much greater forces. So that's why I say that in this case, this is the dominant. It's the dominant force. But it's operative in everything, because wherever we have electrons, they are in motion. So this is the dominant one. All right, so we can look at it in a few other instances. So for example, we can look at it in the case of iodine. We can look at it in the case of methane. All the same, time-fluctuating dipoles. And this is a very, very weak force. So the energy in London dispersion forces, or van der Waals bonds, is proportional to, I'm just going to give it proportional, it's proportional to a quantity called the polarizability. Polarizability. The polarizability is, and this was defined by London, polarizability is a measure of how easy it is to induce this dipole. Okay? A measure of the ease of electron displacement within an atom. Measurement of ease of displacement, ease of electron displacement. Okay? And it depends on, it's influenced by the size, and it's influenced by the number of electrons in the atom. Huh? So what do I mean by that? Well, let's take two systems. Suppose I've got argon, and I'll go up two members in the same series, and I've got helium. So what are the forces that hold helium together? Same thing. But the boiling point here is 87 Kelvin. The boiling point here is 4.2 Kelvin. Why does this have such a low boiling point? Well, polarizability. Size, helium is smaller. So the degree, the corral in which the electrons can roam is smaller. So the extent of electron displacement is smaller. And secondly, there are only two electrons, and they're in 1s, and they're tightly held. And so the delta minus, delta plus capable of being created in helium is tiny compared to the delta minus, delta plus that can be created in argon. So the energy goes as polarizability squared and divided by r to the sixth, where this is the separation, not the radius, but this is separation. Separation, dipole separation. And this is a font issue. This is proportional to alpha. So you can tell the difference. This is a proportional, that's to alpha. Of course you can't tell the difference. You can't. This is a contextual. If I just wrote this by itself, you don't know what it is. My goodness, you're nervous. You're so nervous. All right, let's take a look at, here's the cartoons, induced dipole, and here's London's paper. Here's London's paper as it first appeared in 1930. Theory and System of Molecular Forces. And here's some cartoons from your book. This is helium, showing helium. It's kind of funny how the artist shows, like there's these two helium atoms, and they're absolutely immobile. And all of a sudden, one of the helium atoms starts jiggling, and then it induces a dipole moment in the other one. That's not how it happens. But anyways, that's... All right. This is hydrogen. Same thing as iodine. All right. So there's delta plus, delta minus, because the electrons are moving, even though there's a strong covalent bond inside. So let me just make the point. I want to make sure people are very clear about primary versus secondary bonding. So if I look at iodine, I2, this is a covalent bond. It's homonuclear. This is covalent bond. There's no net dipole moment. Here's another iodine. But then we have time-fluctuating dipoles. So this delta minus isn't because this is the bond here. This is the primary bond. This is the primary bond, and it's covalent. And this is the secondary bond. And the secondary bond is London dispersion force or van der Waals bonds, because this is induced dipole. There we go. Good. All right. So now let's look at, here's another one. This one gets on my nerves. Actually, this is good. This is good. This isn't the bad one. All right, so I want to show you polarizability. So here's a series of sp3 hybridized chains, propane, octane, icosane. So they're all the same. They look like this. CH is sp3 hybridized. And so you just have, so what is that? C3H8. So it's just, see, you have 1, 2, 3, 4. So there's hydrogen, hydrogen, hydrogen. And then the fourth one, I'm going to make it flat instead of trying to make a tetrahedron. All right? So 1, 2, 3 hydrogens. The fourth one is carbon. 1, 2 hydrogens, carbon, carbon. 1, 2, 3 hydrogens. So this is C3H8. And compare that to the longer one, all right, which is octane, which is C8H18. So it's 1, 2, 3, 4, 5, 6, 7, 8. And all you got to do is 1, 2, 3, 4, 5, 6, 7, 8. And you put 4 sticks off of every carbon. You can't go wrong. You count them up. You got C8H18. Now look at the structures. They're the same. So how come propane is a gas at room temperature, whereas octane, which is the principal constituent of gasoline, is a liquid at room temperature? It all comes down to polarizability. This one's got a longer corral. So if you like, the delta minus versus the delta plus is basically the same here, except the separation is bigger. Right? All right, so that's pretty good. That's pretty good. This is the one that gets on my nerves. You see this? It's exactly what I just showed you. So here's methane, and there's the propane. Here's butane, and somewhere between butane and pentane, we cross the line at room temperature. So pentane is liquid, butane is gas. And you keep going up, 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 and finally, if you get to C20, you go from liquid to solid, because now the van der Waals forces are strong enough that even at room temperature, you make a solid. It looks like paraffin. Okay? That's why you can melt paraffin, because it's got weak van der Waals forces. So temperature disrupts and it reforms. If you try to break a covalent bond, you pyrolyze the thing and you don't get it back. Secondary bonds allow for ready processing. Here's what bothers me about this. Instead of talking about polarizability, which is a physical quantity that means something, they say molecular weight. Well, it's true that this scales. These are heavier and it's monotonic. But to me, what's the relevant physics between the ability to form van der Waals bonds and the mass? It's a dumb thing. It's not a gravitational effect, so that's why this thing is stupid. And you see it all over in chemistry books, and it's just dumb. And if you put that on my exam, you're not going to get points for it, because that's dumb. All right. Okay, let's go to the next one. There's a third type of bonding. There's a third type of bonding. Yeah, there's certain things I feel strongly about. That's one of them. Okay, so let's look at the third type of secondary bonding. Third type of secondary bonding is called hydrogen bonding. Hydrogen bonding. It's a type of secondary bonding, and it occurs between hydrogen. It occurs between hydrogen and the most electronegative elements, fluorine, oxygen, nitrogen. Well, why these? Because they have very, very high average valence electron energy. So the average valence electron energy, I'm quoting in that second column, not in megajoules per mole, but in sensible units like electron volts. And so you can see when you get up around 18, 19 electron volts, you cross a threshold. And then that's the electronegativity as represented by average valence electron energy. So you can see that as the electronegativity gets beyond some threshold value, roughly 3, then you can form hydrogen bonds. So this is owing to high average valence electron energy, or if you like, electronegativity, which means very strong polarity in the covalent bond. In the covalent bond. Okay, so you say, well, there's polar and there's even more polar. So let's see what happens. So I'm going to use a prototypical value here. I'm going to look at HF. So if I look at HF, let's go through the Lewis structure. There's H with its 1 electron, and F with the 7. 1, 2, 3, 4, 5, 6, 7. And so we have the covalent bond here, and we know fluorine is the most electronegative. So we have a dipole moment here. Now, the dipole moment is very strong here, and this is an accounting procedure to put the 2 electrons, but it in no way represents the physical position of these electrons. They're brought in very close to the fluorine, so it's not symmetrically disposed between the H and the F. So I can't tell anything about whether HF is a solid, liquid, or gas. Why? Because there's only one sitting here. I got to put at least one more because this is a primary bond. And it tells me how H bonds to F. It doesn't tell me how one HF bonds to another HF. So I'm going to put another HF over here. So there's another HF. And this also dipole. But there's something special about this. Already there's a dipole-dipole interaction. But the hydrogen bond is much stronger. It's much stronger. And why is it stronger? The electron in this hydrogen on the right is pulled towards the fluorine to such an extent that this hydrogen is so denuded of its electron that it's acting as proton-like. It's proton-like. Now, don't tell people that Professor Sadoway said that hydrogen inside of HF is a proton. It's not a proton, but it's starting to get more nearly like a proton. And what do we know about a proton? Positive charge, tiny, high charge density. So this hydrogen's looking forlornly over at at its electron. It's being hogged by the fluorine to the right. And what do we know about these? Oh, it's time for colored chalk. It's time for colored chalk. What color are those? They're red because they're non-bonding. And the bonding are the blue in between. And what do we know about the volume occupied by a non-bonding pair versus a bonding pair? It's larger, right? Because they're not constrained. So not only do we have a non-bonding pair, they're not just here, they're sort of flopping around, hanging way out. And there's this thing here that's denuded almost of its electrons, so it starts looking over here saying, if I can't get any action over here, what about here? So the proton starts establishing contact with the non-bonding pair of electrons on the adjacent fluorine. And this is the hydrogen bond. The hydrogen bond is here. The hydrogen bond is not here. If you write this, I will give you 0. I'll give you a 0 with a circle around it. It's called the donut. That's what you get when you write something so stupid. This is not the hydrogen bond. This is the hydrogen bond. Okay? So it works. It works. Now let's see the effect of it. Let's see the effect. All right, so here's a cartoon showing in water, the hydrogen-oxygen spacing is about 1 angstrom, and the hydrogen-oxygen spacing in adjacent water molecules can be less than 2 angstroms. So there's certainly a difference. I mean, it can't be the same. If it were the same, it would be a covalent primary bond, and you'd have a network. Now, this is interesting here because this shows the values that are given on your periodic table, which were obtained without the use of the average valence electron energies. These trends are correct, but look at this one. They got chlorine up at 3.16. And all of these have been revised. Now, on a test, just use what you've been given on the periodic table, but I want you to understand how this is rationalized with better data coming from photoelectron spectroscopy. So now I want to show you the implications of hydrogen bonding. The implications. So I've got 4 homologous series. So they're all element plus hydrogen. So let's start with the group 14. That's shown here in purple. Group 14 shown in purple. And what do we have? All of these, we'll start with methane, CH4. So that's a central atom, 1, 2, 3, 4. They're all tetrahedral. Hydrogens at the corners, nonpolar, and no hydrogen bonding capability. So one methane bonds to another methane by weak van der Waals forces. That's how it does. And it doesn't matter if I substitute the carbon with silicon or germanium or tin. I can put SNH4, and how does SNH4 bond to another SNH4? It's just by London dispersion forces. That's all that's operative here. And so we have what makes sense here, that the heavier, more massive, no, the ones that have greater polarizability have a higher boiling point because their van der Waals forces are stronger. That means you have to go to a higher temperature to achieve disruption. Same temperature, weak van der Waals force, gas. Same temperature, strong van der Waals force, liquid or solid. And you see the boiling point here. Monotonic from the lightest to the heaviest. Now let's go to the next one. Let's go to the green line, group 15. Well, group 15, what's that look like? Well, let's look at the structure of group 15. Group 15 is ammonia is one of them. So we can look at the structure of ammonia, and if we use Vesper, we'll end up with something that looks like this. I'm going to go through the whole thing. You're going to end up with 3 bonds like this. It's a tetrahedral skeleton with a lone pair. Colored chalk. So now, what happens? I can't say anything about this. Why can't I say anything about whether this is a solid, liquid, or a gas? There's only one there. We've got to put another one. So I'll put another one up here. N, H, H, H. Same gambit as with the hydrogen fluoride. This hydrogen sees this lone pair and establishes a hydrogen bond. And that adds to what otherwise would have been a dipole-dipole. This has a net dipole moment, agreed? So there's a dipole-dipole moment here, but this bond is even stronger. The hydrogen bond is even stronger than dipole-dipole interactions. So now let's look at the graph up here. So what about in phosphine, pH 3? No, phosphorus isn't electronegative enough. So in phosphine, in arsine, and in stibnine, we don't have hydrogen bonding. So you see this series in the group 4 here? It goes monotonic from the heaviest element down to the lightest element. But here, heaviest, less heavy, and the lightest element that should be down here is up here. Why is the lightest compound not down here? Because of the addition of hydrogen bonding. So ammonia is off the line. This line shows the trend based on dipole-dipole interactions only. Right? And you can see the difference. See, if you have van der Waals forces alone versus dipole-dipole are stronger, so SNH4 has a lower boiling point than SBH3. I can't predict this, but I could ask you, if I gave you this data, say, can you explain this to me? Let's keep going. Let's go to group 16. So telluride, selenide, sulfide, the oxide, H2O, water, it should have a boiling point of -100 centigrade, were it not for hydrogen bonding. How does water work? Well, again, sp3 hybridization, oxygen, 1, 2, 3, 4, 2 lone pairs, 1, 2, H, H. And now what happens? I bring another water molecule over here, and hydrogen bonding. And that hydrogen bond raises the temperature, raises the requirement for thermal disruption, and moves the boiling point of water up to 100 degrees Celsius. If it weren't for this, we wouldn't have this conversation, because we wouldn't have evolved as a species capable of conducting business at room temperature if water boiled at -100 Celsius. Hydrogen bonding is critical. It's absolutely critical. So, now you know. And this isn't just some little bit of pedantry for a professor. This is very important, because we are going to learn later that when it comes to the biochemistry, we will appreciate that most biochemicals are made of carbon, oxygen, nitrogen, and hydrogen. And that means you can have hydrogen bonds here, and you can have hydrogen bonds here. Hydrogen bonding is critical to life. So this is a very important thing to know about. Okay, we have a minute or two. Yeah, so you can see polarizability increases here, but hydrogen bonding operative here. Explains the mystery. All right, we're going to jump over this because we are out of time. And so I will simply show you a few pictures. So this is a conference in Copenhagen in June of 1936, and there's Fritz London. But look at who else is at the conference. Niels Bohr, Wolfgang Pauli, Werner Heisenberg, Max Born. Remember the Born exponent? You better remember it for Wednesday. This is Lisa Meitner. You haven't met her yet. We'll get to her. This is Walter Stern-Gerlach. And this is James Franck. That's just the first 2 rows. This is quite a conference. Here's a picture of Fritz London sitting on a bench in Berlin with Erwin Schrödinger. Right? Schrödinger is brooding. He's thinking. Fritz London is smiling. You know why? Because he's figured it out. It's time-fluctuating dipole, but he's not going to tell Schrödinger. He's going to say, you have to read about it, but you have to go to the library, because if you don't read the primary sources, if you go to Wikipedia, you won't find this, because it's not going to be in Wikipedia in 1913. Yeah. Okay, and last thing, hold on. Hey, wait a minute, where are you going? We're not done yet. Did the professor say class dismissed? No. So here's a biography of Fritz London, which, I would recommend if you have a few minutes and you'd like to unwind, go out, sit in the sun, and read something like this. It tells the story of how he came up with these ideas, the rise of fascism in the 30s. He comes to the United States, takes a teaching position at Duke University. All of the people that he met along the way, all these people that we study, all this stuff, it's all there from his perspective and the perspective of his biographer, plus the pictures. So, anyways, primary sources. Go read the primary sources. All right, class dismissed.